All right, today we are diving deep into a really cool topic, distributed breadth first search. This is the powerhouse algorithm that lets us make sense of absolutely gigantic networks. Have you ever stopped to think about how your GPS can find the quickest route across a huge city in like a split second? Or how a social network can instantly show you the shortest path to some friend of a friend? Well, the secret is a clever algorithm. But when the map gets as big as the entire internet, that algorithm needs a serious upgrade. So, here's our game plan. We're going to start with the basics, the classic breadth first search, or BFS. Then we'll look at why that simple approach just completely falls apart at a massive scale. After that, we'll bring in a team, look at 2 different ways they can split up the work, and finally, we'll see which strategy actually comes out on top. To get started, let's imagine a single, lone explorer who's trying to map out some new territory. Now, to do this efficiently, they need a strategy. And in the world of computer science, that strategy is called breadth first search. BFS is actually beautiful in its simplicity. Think of our explorer. They're standing in a room. Instead of just picking one door and going through it, they first check every single door in that room. Only after they've checked all the doors on their current level do they move into the next hallway. By doing this, by exploring level by level, it guarantees you'll find the shortest path first, as long as every step has the same cost. So, how does this actually work under the hood? Well, you start at one spot, a node, and you put it in a line, or a queue. Then you take the first item out of the line, look at all of its immediate neighbors that you haven't seen yet, and you add them to the back of the line. Then you just repeat. You take the next thing from the front of the line and do it all over again. This whole first in, first out system is the key. It's what forces the algorithm to explore everything 1 step away, then everything 2 steps away, and so on. Okay, so this lone explorer strategy is perfect for a regular-sized map. But what happens when that map isn't just a small cave system, but a graph with billions and billions of points? Well, the whole strategy just hits a wall. Hard. And I mean, we are talking about a scale that is just hard to wrap your head around. Think about the entire World Wide Web with all its links or every connection on a huge social network. These graphs can have over 1 billion vertices, that's 1 billion locations, and 10 billion edges connecting them. Our poor lone explorer, our single computer, just doesn't stand a chance. And here's the real kicker. The problem isn't just that it would be too slow. As this paper points out, a single machine often doesn't even have enough RAM to hold the entire map in the first place. It's a fundamental hardware problem. So if one explorer isn't going to cut it, what's the solution? You guessed it. You bring in a team. In the world of computers, this means using lots of processors, all working in parallel. But to do that, they need a whole new coordinated way of searching. The single most important idea for this team of explorers is something called the frontier. Just picture it as the collective edge of everything they've explored so far. The goal is for all the processors to push this frontier outwards together, 1 level at a time. It's like a synchronized wave moving through the graph. Okay, so here's how the team stays in sync. Each processor works on its own little part of the frontier. When it finds a new, unexplored neighbor, it sends a message, like a little walkie-talkie update, over to whichever processor is in charge of that new spot. That processor then adds the new location to its to-do list for the next big push. It's this constant communication that keeps the whole thing moving forward together. But wait, before the team can even start exploring, they need a plan, a really important one. How are they going to divide up this massive, planet-sized map in the first place? This is a process called partitioning, and there are 2 main ways to do it. The first strategy is called 1D partitioning, and it's probably the most intuitive way you'd think to do it. You basically just divide up all the locations, the vertices. You give one group of vertices to processor A, another group to processor B, and so on. It's like taking the map and cutting it into a bunch of long vertical strips and giving one strip to each explorer. The second strategy is called 2D, or checkerboard partitioning. Now, this one's a bit more complex. Instead of dividing up the locations, you divide up the connections between them, the edges. Imagine laying a giant grid over your map. Each processor is now responsible for all the connections that fall inside its little square of the grid. So let's compare them head to head. 1D splits up the locations, the vertices. It's simpler to set up, but it can lead to a ton of communication between processors. 2D, on the other hand, splits up the connections, the edges. It's definitely more complex to manage, but it holds the promise of seriously cutting down on all that chatter. So this sets up the big question. Which one is actually better when it counts? All right, we have our two competing strategies. Now it's time for the main event. Let's dig into the data from the research and see which of these approaches actually holds up when things get really tough. So here it is, the million-dollar question. When you're trying to search a graph with a billion nodes, which strategy for dividing up the work is going to be faster and more efficient? And this chart right here tells us everything we need to know. It's plotting the communication cost against something called average degree, which is basically just how connected the graph is. So a social network where people have lots of friends would have a high average degree. Now look what happens. As the graph gets denser and more tangled, that bar for 1D partitioning just shoots sky high. The communication overhead gets crazy. But look at the 2D bar. It stays so much lower. For those really complex, messy networks, 2D partitioning is the hands-down winner. It's not even close. So let's wrap this all up. What are the big takeaways? 1. For the huge planet-scale graphs we use today, you absolutely need a distributed approach like this. 2. How you split up the work, your partitioning strategy, is incredibly important for performance. 3. For those really dense, highly connected graphs, 2D partitioning is way, way better because it keeps communication under control. And finally, the good news is that both of these methods are scalable. You can just keep adding more processors to tackle bigger and bigger graphs without hitting that memory wall. So we've figured out how to map graphs that are truly massive. But data is not slowing down. It's getting bigger, more complex, and changing faster every single day. So the real question to think about is, what's next? What new challenges are just over the horizon that will force us to invent the next generation of these amazing algorithms?